Let's discuss surface area involving parametric curves. If we want to look at our parametric version of the arc length formula, we saw in our last video that a little bit of arc length ds can be described as the following. So I want to describe my parametric curve like this. X of t is equal to f of t, y of t is equal to g of t, and we have our t is bounded between alpha and beta. When we have such a situation, we can write our ds, which is that little bit of arc length, as the square root of df dt squared plus dg dt squared dt. So this was that little bit of arc length that we had talked about last time. Now, what we want to do is we want to basically take this curve and we want to rotate it about either the x-axis or the y-axis. So let me pause for a second so I can draw a couple of curves. Hold on. And we're back. Okay, so here you can see I've drawn a couple sets of axes and I have my parametric curve in blue over here. And I want to look at the two situations. One situation is we rotate about the x-axis, and the other situation is we rotate about the y-axis. So we have rotating about x-axis, and we have rotating about the y-axis. And I want to remind you that when we're talking about surface area, these both sort of come from the same equation. So what's that equation? That equation for surface area was going to be the integral of 2 pi r ds. Now, this 2 pi r, that was the circumference of the circle. So we have the circumference of a circle coming around like this, or coming around like this. And then the ds was that little bit of arc length that we had discussed earlier, like this. And we know that everything is going to be parameterized in terms of t, so we're going to need an alpha and a beta. Okay, so this was our general formula for surface area. So let me maybe put a is equal to that, like this. And then I want to get into more specifics. So if you're talking about the x-axis, then the formula is going to be the integral from alpha to beta, 2 pi. Now remember, the radius is always perpendicular to the axis of rotation. So what that means is this should be the y value, and the y value is given by g of t. Okay, so I'm going to put g of t over here, and I'm going to remind you that this was y. And then we just have our ds piece. So our ds piece is this square root of df dt squared plus dg dt squared dt. Okay. So one of the things I like, actually, is a quick aside, is I like how this ds kind of looks like a Pythagorean theorem involving sort of first derivatives. I think that's kind of cool. Okay, let's go back to our other case. Our other case was rotating about the y-axis. So when you rotate about the y-axis like this, your circle is going to come over here, and then your radius is actually going to be the x value. And we know that our x value is given by f of t. So when I go to write my formula for rotating about the y-axis, that's going to be the integral from alpha to beta. This is going to be 2 pi f of t times the ds piece, which was the square root of df dt squared plus dg dt squared dt. All right, and just as a quick reminder, this is our x which is perpendicular to the axis of rotation. So I'm going to highlight both of these formulas. These will be what we use to solve our problems. And that's rotating about the x-axis. And then this bottom one is rotating about the y-axis. All right. Let's take a look at an example. Let's look at example 5. Okay, so here's example 5. It says calculate the surface area, and then they give us this parametric curve. I can see that x is equal to t. So that's really basically saying x is like identical to the independent variable. So if I made a substitution of x for t, I would get y is equal to t cubed. And we're having t go from 0 to 1 about the x-axis. So basically, we're taking this region, this part of the curve right here, and we're rotating it about the x-axis. So I'm going to put a little loop to indicate, okay, we're going around the x-axis like that, okay? So feel free to pause the video and take a moment to draw that picture if you need to or want to. Okay, so we have our parametric curve, and we know we're going to need dx dt and dy dt. So dx dt, that's going to be equal to just 1, and dy dt, that's going to be equal to 3t squared, like this. All right? And we know that we are going to rotate about the x-axis. So our formula for the area, it's going to be A is equal to the integral from alpha to beta. In this case, alpha is 0 and beta is 1. It's going to be 2 pi. Remember, we are rotating perpendicular, or the radius is going to be perpendicular to the axis of rotation. So in this case, the radius will be given by the y value. And in our case, y is t cubed, like so. And then we want to multiply by the ds part. So the ds part is really dx dt 1 plus dy dt squared. That's going to give us 9t to the 4th. And then we have a dt out in front like this. Okay. So when I look at this integral, I see that we have a pretty simple u substitution. In other words, if I let u be the integrand, I'm sorry, the part under the square root here, then I can see the derivative sitting off to the side right there. So we're going to make that substitution. So why don't we let u be equal to 1 plus 9 t to the 4th. This tells me that du dt is equal to 36 t cubed, which means that dt is equal to 1 over 36 t cubed du. We also want to change our limits of integration. So when x is equal to 1, that means u is equal to 1 plus 9 times 1, which is 10. When x is equal to 0, that means that u is equal to 1 plus 0, which is 1. So my integral now becomes the integral from 1 to 10 2 pi. Let's leave the t cubed in there temporarily. Square root of u. And then we substitute in our dt part. That's going to be 1 over 36 t cubed du. So luckily for us, or not luck really, but the t cubed and the t cubed cancel out. So everything is still in terms of u now, which is what we want. When we factor the constants out of the integral, we're going to get 2 pi divided by 36, which is pi over 18. Integral from 1 to 10 u to the 1/2 power du. All right, let us finish off this question. So we're ready to find our antiderivative now. We're going to get pi over 18 u to the, we're going to add 1 to the exponent, so that's going to be 3/2. Dividing by the fraction is the same thing as multiplying by the reciprocal, so that's going to be times 2/3. And we're going to evaluate this from 1 to 10. We do not have to change back because we've already changed the limits of integration. So when we simplify this down, the pi over 18 divided by 2 is 9. 9 times 3 is 27, so we get a 27 here. And then we're going to put as our brackets, when we plug in a 10, we're going to get 10 to the 3/2. And when we plug in a 1, we're going to get minus 1 to the 3/2, which is this 1. Okay. I'm going to tack on a units squared because we're talking about area. I'm going to highlight that final answer here. All right, everybody. Take care.